Hi all, welcome to another tutorial session from Nairo Research. So in this session we are continuing the concept of EDA with some practical examples. So as I said earlier, energy decomposition analysis explains how to perform an analysis of ammonia borane in which ammonia and borane, which is a complex, have a donor-acceptor interaction with each other. So in this example, we can examine that which interaction results in a stable complex. For an example, I'm taking the concept of EDA with restricted fragments. So we will be discussing more about EDA with unrestricted fragments as well as EDA with the natural orbitals for chemical valence for metal complexes. Okay, so let me show you an example. As I said earlier, we will be focusing on geometry optimizations of ammonia, borane, and the amino-borane complex. So let me first open up with an ammonia molecule. Yes, I'm selecting the ammonia molecule. Yes, you can see the structure of ammonia. We are going to start with an optimization. Before that, I'm just symmetrizing the molecule to understand what's the symmetry. So you can see C3V is enforced. And then I'm changing the task to geometry optimization, the XC functional to generalized gradient approximation Wikipedia to 86, and then the basis set to TZP with a single polarization, split by triple theta, single polarization, and numerical quality from normal to good for getting better quality. And I'm just saving this and giving it ammonia. And now, after saving that file, I'm just running it. So we can see the progress of this reaction, this optimization step. So once it is finished, we will be proceeding to the next molecule, borane. We will be repeating the same step. Yeah, this is finished. Okay, fine. So we will be using a new input, or else we can do the same thing in this interface by saving it to another file name, but we are opening a new input. Okay, let's see that how this thing can be calculated. Okay, so let me open up the database, and I'm just searching the ammonium from molecules, and here I'm changing this using the periodic tool. Now it is a borane. I'm enforcing the symmetry, same symmetry, and then I'm changing the task to geometry optimization basis set to GGA, generalized gradient approximation, a higher order basis set, and the quality a little bit good. And I'm running the calculation after saving it. So borane. And now I'm running the calculation. So after finishing, we will be selecting the complex. So we can either do the selection from the optimized structures, or directly we can select the molecule from the input itself. So let it run, and we will go with the new input, and once it is finished, yes, so here we are taking an ethane molecule. It's a little bit slow when we are recording the things. Okay, so I'm just selecting an ethane molecule from the molecular database, and I'm just changing the respective carbon atoms to nitrogen and boron. I'm just enforcing the symmetry, and then I'm changing the task correlation function. Sorry, I had a spelled mistakenly about the previous thing. It is exchange correlation function instead of basis it. And I'm changing it and I'm saving it. Amino _ borane. After that, we are going to optimize this thing. So after finishing the optimization, we will be focusing on a single point energy calculation. So we will wait for some seconds. Once it is finished, we will be proceeding for a single point energy with molecular fragments. It's a little bit faster compared to the previous. So the iterations, once it is finished, we will be focusing on the next step. It will take some couple of minutes. So we can, in the meantime, you can see that it is finished. So now we will be proceeding to the next step. So the new job. So we'll be changing to single point energy calculation. We will be, we are not changing the correlation function as well as the other settings, the workflow. And then we are going to do the modeling, region selections. So here, first I am selecting the amino region. I'm giving it as NH3. And the next region is the borane. So once these two are selected, we will be proceeding to the fragments. In multi-level tab, we are selecting fragments and we are just activating the fragmentations. The fragments as per this calculation. And now we are just going to save it and _ed. So I'm just saving it, and once it is saved, it will take some seconds. So now I'm going to run the calculation. Okay, you can see that what's the thing happening in the backend, which all data it is taking from this optimized geometry. So the job actually runs 3 separate calculations. First, the single point calculations for ammonia and borane in their prepared geometry, which we have already calculated, and the technically the .rkf files of those single point computations are then used for this fragmentation analysis. So I can show you what is actually the archive file from this thing. So this is actually the adf.archive file. So from this files they are going to calculate the fragmentation analysis. So once this is finished, I will show you that results. Okay, fine. So let me show you the output of this fragmentation analysis. So from properties, we can go to bonding energy decomposition, and from this we can find out the exact orbital interactions and the value of this total bonding energy in kilocals per mole. It will comes around minus 44.62. So you can see the Pauli's repulsions, as in the intro session I have said that what are the parameters included in this total bonding energy. So this could be the expected output, and in the next session we will be focusing on the other parts of EDA. Thank you.